Oh, you're right. We're ready to go. Okay, so 244 number 13 says, given that sine x equals cos 3 pi over 11. So I'm just going to write that down here. What is it again? Oh, sine x is equal to cos 3 pi over 11. And that x lies in the second quadrant. Determine the measure of angle x. Okay, now this is the type of question where we've seen now quite a few times, usually in a more complex scenario where we have a sine value equal to cosine value. Okay, so what you should be thinking here is your correlated angle identities, because those are identities that guarantee a sine value being equal to a cos value, and then all the other types of correlated identities we have. Okay, so here now there's one little extra thing we have to keep in mind, is they're telling us specifically that x is going to be in the second quadrant. Okay, so if we look on our formula sheet, you'll see two identities that match this structure. Okay, you're going to see sine of pi over 2 minus theta is equal to cos of theta. So that's one of the identities. And then the other one is sine of pi over 2 plus theta is equal to cos of theta. And if I was just looking for an answer, I could use either one. But here they're specifically telling me that x has to be in the second quadrant. So that might affect which one I choose to use. Now let's keep in mind what these identities tell you. So this identity tells me that if I have a sine expression and the input is pi over 2 minus the input to the cos expression, then these things are guaranteed to be equal. Okay, so here, if this input to sine is pi over 2 minus the input to cosine, then that solves the equation because both sides are guaranteed to be equal. Okay, the problem is that 3 pi over 11, well, this is definitely less than pi over 2. So 3 pi over 11 is in the first quadrant. And so if I do pi over 2 minus 3 pi over 11, I'm still in the first quadrant. Okay, so if this is my theta and this is pi over 2 minus theta, I'm still in the first quadrant. Okay, so that's why I'm not going to use this one here. Whereas similarly, if this is my 3 pi over 11, pi over 2 plus 3 pi over 11 is going to be in the second quadrant. Okay, so like I said, if I was just looking for any old answer that would satisfy this equation, I could use either one of these. They just threw in a little extra thing to think about. Okay, so again, I'm using this identity, and what does this identity tell me? It tells me if the input to sine, which is x, is equal to pi over 2 plus the input to cosine, which is 3 pi over 11, then these two sides have to be equal. In other words, this is going to be a solution to this equation. Okay, and so now it's a little easier than all the other ones we had to solve. The difference is that I needed to think about the quadrant here. So here, I guess it's going to have to be 22 as our common denominator. So this is going to be 11 pi plus 6 pi all over 22. So it looks like this is going to be 11 plus 6, so 17 pi over 22. Okay, and is this in the second quadrant? Well, yes, because pi over 2 would be 11 pi over 22, and pi would be 22 pi over 22. So this angle is definitely in the second quadrant. Okay, so again, a reminder, anytime you see an equation where you have a sine value equal to a cosine value, or the negative of a cosine value, or similarly with tangent, cotangent, you should be thinking about your correlated angle identities. The only difference here is they gave us that extra piece, that extra condition that it had to be in the second quadrant. So I had to use pi over 2 plus theta. Okay, any questions on that? Okay, so in the end, relatively simple compared to a lot of the other ones that we solved. Okay, but with that extra little condition. So if there's no questions, let me move on to the next one on the textbook, which was 245 19A. Okay, and let's see what that is. Oh, it's a It's an identity. So let me just write it out. It's a little long. So here it's saying that secant of x, we want to show that that's equal to something significantly more complex. So 2 times cos x sine 2x minus sine x cos 2x all over sine 2x. All right, so I would imagine I wouldn't get any arguments from anyone that I'm going to start with the right-hand side here, okay? And few people have asked me, like, how do I attack these identities? So first of all, there was no choice, really have to use with the right-hand side. But the two things you have to keep in mind is what you're going to be using is both trig identities and traditional algebra, okay? There's no real algebra to be done right off the bat, but what I do see is I see a sine 2x and a cos 2x, okay? So when you're trying to figure out what identities to use, in some cases, you have no choice. I know I need to turn sine 2x into 2 sine x cos x, okay? And presumably the denominator too, but that's less of a concern because this numerator is much more complicated. Whereas the cos 2x, this is where I have a choice of 3 identities, okay? So before I touch the cos 2x, even if that one came first, even if this was flipped around, I'd probably change the sine 2x first, because one of the things that you want to do is you want to see what's going on near this cos 2x to see if maybe that might give you a hint as to what would be the best of the 3 identities to use. So let me start by doing this here. And normally I probably would just, kind of write the next step, but let me be really clear here. So this is 2 sine x cos x, okay, minus, now this is where, before I make a choice, I'm going to look at what I have here. And I notice that I have a sine x times cos squared x, okay? I already have a sine x here. So now when I think of the 3 possibilities for cos 2x, one of them has a cos squared x in it, okay? So what I think I'm going to do is I'm going to use the one that's going to produce the same term that I have here, because here I have a 2 sine x cos squared x. If I choose the second version of that identity, I'm also going to end up with something that involves a sine x and a cos squared x, okay? So this is my reasoning here, okay? So let me just write it out. So sine x, and so the one I'm talking about here would be 2 cos squared x minus 1, okay? Notice, put brackets around it. And here in the denominator, I might as well expand this to 2 sine x cos x. And the first thing I notice is that there's a factor of 2 in numerator and denominator. Remember, this 2 multiplies everything in brackets. So it's a factor of the numerator. There's a factor of the denominator. I might as well reduce it right away. Okay. So now let's clean up the numerator and see what happens. So here we have 2 sine x cos squared x. Here, if I do this first multiplication, what do I have? I have minus 2 sine x cos squared x. Look how nice that is. Not only is it the same term, they even cancel each other out. And then, of course, I need to be careful with my signs here. This is negative sine x times negative 1. So plus sine x. As we said, these just cancel each other out. And now what am I left with? I'm left with sine x over sine x cos x. Sine x's are factors of both numerator and denominator, and all I'm left with is 1 over cos x, which of course is just my left-hand side. Okay, so again, what was my reasoning? Sine 2x, no choice. I had to turn it into 2 sine x cos x. For this one here, I tried to choose the one that would work best with the other terms nearby. And, one thing that works well with other terms nearby is something that's exactly the same type of term. Okay, yeah, Mitchell, question?
I just had, it's like sort of a question, but I did it a slightly different way. If you look at the bracket on the right side, right at the beginning, it is a double angle formula. Like you can just you can turn that whole bracket into two sine x, and then two sine 2x minus x, what it turns into.
Beautiful. That's probably even faster. Oh, beautiful. That's really nice, because here, what Mitchell noticed is that this is exactly the sine formula for a subtraction. Okay. And if you want to write it in a more familiar form, you know, you realize this sine and cosine. Ah, good catch on that one. I didn't even see that. So here's sine 2x cos x. So sine of the first times cos of the second. Okay, minus cos of the first times sine of the second. And this is just equal to, well, what is this? It's sine of the first minus the second, 2x minus x. Okay, using the compound angle formula. And look at that, much, much easier than what I did. See, there you go. Sometimes you might take a route that's a little longer, but as long as you're using, you know, if you're doing everything correctly, you know, somebody who even changed this into, you know, cos squared minus sine squared likely would have gotten to the right answer at one point. Okay, but I will agree with you, Mitchell, that is actually a much more elegant answer than the one I have. Okay. So you're seeing here different ways to look at these problems, okay? And here, what I didn't do is I didn't look for that pattern right off the bat, that this looks a lot like one of our compound angle formulas, okay? Any questions on this here? So here you've got a very elegant answer, because obviously that's just going to cancel out with the signs, and a slightly less elegant answer, but it worked nonetheless. Okay, so if there's no questions, let's move on to the assignment sheet. So let me just bring up the assignment sheet. And somebody had asked for number 2. So here, this is unit 4 assignment sheet. And this is number 2. Okay, so it's a bit of a long question here, so I'll just read it out. Hopefully you have it in front of you. It says 2 gears work together. The smaller gear has a radius of 5 centimeters. Larger gear has a radius of 12 centimeters. Determine the number of radians that the larger gear rotates when the smaller gear rotates by 300 degrees. Okay, so I think the best thing to do is for me to draw a picture, but I'm not going to actually draw gears. I'm just going to use circles. Okay, so we have a smaller one and a larger one. There you go. So as the smaller gear turns, so you got to think a gear with teeth, as the smaller one turns, it makes the bigger one turn. Okay, and I'm just going to see if I've got something circular here. This is kind of circular. And here, this is, that's a bit too big. Oh. Here, let's see if this works. I guess they're kind of similar size here, okay? But even though one might be smaller, as they turn, you notice that there's something in common. What do they have in common as they turn? Because say the smaller one's going to have to turn faster than the bigger one. But what are they going to have in common when these 2 gears turn? Can somebody tell me what they're going to have in common? Yeah, Mitchell again.
The A value is going to be the same.
Yeah, the distance that they travel around, along their edges, because you see they're touching each other. So the distance that's traveled along the edge is going to be the same, which of course we think of as the arc. So the angles are not going to be the same. Clearly the small one, as it moves, okay, is going to, you know, a bigger angle, but the bigger one, smaller angles, but the amount that they move, okay, this length is going to be the same as that length as the 2 circles move around. Okay, so what that does is it gives us something common. And just to, you know, remind you of the types of questions you would have been solving in the past, is say you had, you know, 2 triangles and you had a lot, let's say you had 2 pieces of information for this smaller triangle at the bottom, okay, and only 1 piece of information for this bigger triangle, well, what did you have to use in order to solve the problem? Use what they have in common. So once you find the hypotenuse of this first triangle, you can now find information about this triangle above. Same thing here, is this arc is going to be the same on both circles. But what do they have that's different? Well, this has a radius of 5. This has a radius of 12. And what is it that we have that brings together? Okay. Because here you have the angle, you know, that angle is 300 degrees. Well, you have a formula, and what you're looking for is the angle on the bigger circle. And what you have is the arc length formula. Okay. It's a formula that brings together an arc length, the radius of the circle, and the angle that it makes. Okay. So if I can find the arc length of the smaller circle, it'll be the same as the arc length of the bigger circle. And then I can use this formula to calculate theta. There is one very important condition, though, on this formula. What is the condition in order for this formula to work? It doesn't work in every single circumstance. A very specific thing has to happen. Yes, Samantha. Oh,
Yeah,
sorry. Yeah.
that wasn't me. I don't know. You have to put the degrees, like the theta in radians.
There you go. This formula only works if the angle is in radians. Okay. So here, before I can calculate this arc length, I got to take this 300 and turn it into radians. And you know, if you want to memorize how many radians there are in 1 degree, you can do that. Or what you can always do is set up your, you know, ratio. Pi radians to 180 degrees is equal to, well, x radians to 300 degrees. Okay. So this proportion always works as long as you get your numerators and denominators in the right spot. So if you have your radians in the numerator, here radians has to be the numerator, similar in the denominator. So here, what do we have? We have x is equal to 300 pi over 180. And so here that those go, I guess these are both divisible by 6. So this is 5, this is 3. So it looks like x is equal to 5 pi over 3. Now you might be saying, why don't you just approximate? And of course I could, but if I can, I'd like to save the approximation for the very end if I can. Okay, so now let's find the arc. So I don't even need to say, you know, that it's the small circle, because I know that the arc is going to be the same in both of them. So that's going to be r, which is 5 times theta in radians, which is 5 pi over 3. So that's 25 pi over 3. Again, I'll wait till the end to approximate. Okay, and now what am I looking for? The angle in the first one. So I'm just going to rearrange this as theta equals a over r. So here the arc was 25 pi over 3. My r was the radius 12. Okay, so here this is 25 pi over, I guess 3 times 12 is 36. Okay, and this is in radians. And do they ask me in degrees or radians? No, it says determine the number of radians. So I don't have to switch this back into degrees. Okay. And of course, here it would be reasonable to look for an approximation since we're dealing with an application. So if you did want to, you know, 25 times pi by 36, so it looks like it's about 2.2 radians. But you might as well give it an exact values. Okay. So again, here the idea was to see that the relationship that existed between the two scenarios was that the arcs would be the same, and then you use the arc length formula from one to then apply to the other. Okay. I don't remember who asked that, so let me know if there's any questions. Otherwise, we'll move on. Nope. Okay, let's move on. So the next one I have here is number 8. Number 8 on the assignment sheet. So this is unit 4 assignment number 8. So let's see what that says. It says the angle 2x lies in the third quadrant. So I might as well start drawing myself a picture. So there's third quadrant, there's 2x, such that cos 2x is equal to, so cos 2x is equal to negative 6 over 15. Okay. So A is, sketch the location of the angle 2x. There you go, already done. A is done. It says determine the quadrant of angle x, and then C says find an exact value for cos x. So right away, I know they're asking me for cosine of x, and I'm given cos of 2x. What I'm hoping you think right away is, hey, wait a minute, there's one of the double angle formulas for cosine that only has cosine in its equation. Okay, so in my head, I should already be looking at this formula here. Okay, and of course, the cos x is squared. So when I'm solving for cos x, the thing I'm looking for, I'm going to have to take a square root. So I guess that's why they're asking me what quadrant x is in. Okay, but again, this is one of those questions where I'm going to have to try to determine all this information without actually knowing what x or 2x is equal to. So what we know is that 2x lies somewhere in quadrant 3. Okay, and the trick I'm going to use to figure out where x is in is I'm going to say, well, what's the minimum value that 2x can have? 2x has to be bigger than pi. Okay, and it has to be less than 3 pi over 2. Okay, so essentially 2x has to be less than or equal to, actually not less than or equal to, if it's in the quadrant, I guess it should be strictly less than, has to be less than 3 pi over 2 and greater than pi. Okay, but hey, this is just a linear inequality, which we know how to solve. So x, in order to solve either of these inequalities, I can just divide both sides by 2. Okay, no problem with the inequalities because 2 is a positive number. So x has to be less than 3 pi over 4 and greater than pi over 2. And even if you don't think of it in terms of an inequality, it just makes sense that if the smallest value 2x can be, then is pi, then x has to be bigger than pi over 2, half of that. And if it has to be less than 3 pi over 2, then x has to be less than half of that angle, which is 3 pi over 4. So that means the angle lies somewhere in this area here, between pi over 2 and 3 pi over 4. But of course, the important thing is that it's in the second quadrant. Okay. I mean, they could have asked me for a little more detail, but all they wanted was the quadrant. I actually can give even more detail than that. All right. Any questions on that portion? Okay. So if not, let's take a look at C. And so C now, I'm going to use this formula. Cos 2x equals to cos squared x minus 1. If I was looking for sine of x, I'd be using the one with sine, of course. But here I know this is negative 6 over 15. And now I'm just going to solve for cos x. So first I'll add 1. So negative 6 over 15 plus 1, which is 15 over 15. So here, what is this? Negative 6 plus 15 is my brain's gone numb here. Negative 6 plus 15 is 9. 9 over 15. There we go. I guess here we're going to divide by 2. So 9 over 30 is equal to cos squared x. And so cos x is equal to plus or minus square root of 9 over 30. But of course, now that we know that x is in the second quadrant, I know that it has to be the negative square root. So here, we have that cos x is equal to square root of 9 over 30, which I should clean that up, of course. I should not leave it as 9 over 30. It's 3 over 10. Okay, sorry, negative root 3 over 10, since x is in quadrant 2. Okay. Yeah, Samantha, go ahead.
Sorry, I should have asked this before, but I'm still a little bit confused about how you determined it was in quadrant 2. Like, I still kind of don't understand.
So here what I did is all they told me about 2x is that it's in the third quadrant. Okay. Now third quadrant's pretty big. So what I told myself is that if it's in the third quadrant, the angle 2x has to be bigger than pi and less than 3 pi over 2. Are you good with that?
Yeah.
So if I'm looking for x, that's just half of that. So how can I solve a linear inequality? I can just solve for x with opposite operations, like we learned how to do a couple of units ago. Since 2 is a positive number, I can divide both sides by 2. Doesn't change the inequality. And of course, you do the same thing with that other inequality. So I just divided both inequalities by 2. So now this tells me that the angle x has to be bigger than pi over 2, which is here, and less than 3 pi over 4, which is here. So that means it lives somewhere in this area here, which is in the second quadrant.
Okay, I understand. Thank you.
Okay, great. All right, any other questions on this one here? No, okay. So let's move on to, somebody had asked for the third identity on this one here. Yeah, and that's a bit of a nice one. Okay. So here we have unit 4 assignment, and this is, I'll call it 10C. Okay, and so here we want to prove that sine x minus sine 3x over cos x plus cos 3x is equal to negative 10x. Okay. So again, I think we can all agree there's no doubt as to which side we're going to start with. So we'll start with the left-hand side here. And this is where we come up to something that's a bit different, you know, because we certainly deal with sine x and cos x, sine 2x, cos 2x. We've seen that lots of times. But what do we do with sine of 3x? So we don't have a formula, direct formula for sine of 3x, but this is where I'm going to use, you know, inspiration from the past. So how did we determine a formula for sine of 2x? We wrote it as x plus x. So here, I'm just going to write 3x as 2x plus x. Okay, because then I can apply my addition formula. And I guess I'm just going to do the same thing for cosine. So it's really the only, you know, obvious thing I can see to do here. Okay, although, hey, last time I didn't see something really easy. So anybody else see something really easy that I missed? Speak up now. No? Okay. So let's go ahead and do this. So sine of x minus, and of course, be very careful to open up those brackets. So here, I'm going to write this as sine of, okay, let me write, I was going to try to skip a line, but let me just write it out. Let me write this out as sine of 2x plus x. Okay. Just so that we're very clear as to what's happening here. So cos of 2x plus x, and now I'll expand. Okay, so sine x. So as I said before, anytime I'm replacing something, put it in brackets. Okay, not so important in the denominator, but very important in the numerator. So here, what is this? It's sine sine of the first times cos of the second, plus sine cos of the first, sine of the second. Oops. Cos of the first, which is 2x, times sine of the second, which is x. And I'm going to do the same thing in the denominator here, cos x plus, okay, so this is cos of the first, cos of the second, minus sine of the first, sine of the second. Okay. So now this is where we've got to make some decisions, okay? And so obviously here we do recognize this as an addition formula, but obviously we don't want to go backwards. So we're not going to do, what was suggested before. So this is where, again, I'm going to focus on what do I have a choice with and what do I not have a choice with. Okay, so I'm going to distribute this out just so that I get everything correct. So here I know there's no choice but to turn this into 2 sine x cos x, and then I've got my other cos x. Oops, just cos x. I'm thinking about the next step here. Okay. And now for the second one, this is where, again, I'm going to make my choice very carefully. That here, since I have a sine cos squared x, and I already have a sine x, I'm going to choose to use. So first of all, make sure you're distributing the negative. I'm going to choose to write this as 2 cos squared x minus 1, okay, times sine x. Okay. Why? Because when I multiply this out, what am I going to end up with? I'm going to end up with a sine cos squared like I have here. Okay. And again, folks, please make sure you're keeping track of my algebra here. Okay, so cos x. And so now let's see what happens with this one. Even though the cos 2x comes first, I'm going to think about this second term here. Okay. All right, so I'll even write it out here. 2 sine x cos x, okay, times sine x. And what do I end up with this one here? I end up with 2 sine squared cos, whereas here I already have a cos. So guess what I'm going to do? I'm going to replace this one with the one that has sine squared. Okay. 1 minus 2 sine squared x, okay, times cos x. Okay, so any question on the choice that I made? Notice how I changed the one where I had no option. And then once I did that one, that inspired me to choose the one for the cos 2x. Okay, so that I'm not just choosing without a strategy. All right, so now let's try to clean this up here and hope that things work out nicely. So here we've got minus 2 sine x cos squared x. Okay. Here we have a minus 2 sine x cos squared x. So not as nice as before. They're not canceling out, but at least we can, we know we can bring them together. And then here minus minus, so plus sine x. Okay. And here, let's do the denominator here. We've got cos x. Here we've got plus cos x. And then here we've got minus 2 sine squared x cos x. And then here we have another minus 2 sine squared x cos x. Okay. So again, it looks awful, but we're starting to see that there's quite a few things that come together. So I have a sine x plus sine x, so 2 sine x. And then here I've got minus 4 sine x cos squared x. Okay, and the denominator, cos x plus cos x, 2 cos x. And then here we have minus 2 minus another 2. So that's minus 4. What is it here? Sine squared x cos x. Okay. So already it's looking better. Kind of got really ugly. Now it's getting a little better. Now I do notice here that I've got a common factor of 2 and a common factor of sine x. So I think it makes sense to factor that out. So this is where now I'm using algebra, not using trigonometry. So what are we left with? We're left with 1 minus 2 cos squared x. Okay. And then here we're left with, okay, there's still a common factor of 2, common factor of cos x now. And then here we're left with 1 minus 2 sine squared x. Okay. So this is pretty nice. The 2's cancel out. I see a sine x over cos x, but the other side has a negative tan x. I've got a tan x, and this is negative tan x. So that's going to give me some, hopefully some inspiration as to how to deal with what's left over, because obviously these are not the same. They can't cancel out, but I'm hoping both of these things look very familiar. So let's start with what I would say is the easier one. What is that denominator equal to? Who's going to tell me what that denominator is equal to? Anybody? That's pretty straightforward.
Cos of 2x.
It's just cos of 2x. Now this numerator is not equal to cos of 2x, but it looks a lot like cos of 2x. What's the only thing that's different about this here? Anybody tell me the only thing that's different there?
First, you need to factor out negative.
There you go. You realize this is negative 2 cos squared x minus 1, which is negative cos 2x. And there you go. They do cancel out, but you got this negative that's hanging around. So negative tan x, which is your right-hand side. Okay. Now, is this the type of identity you would get on a test? No, this is not the type of identity you get on the test, but it's kind of a really nice one to see whether you can kind of see everything through, to see if you can recycle a trick that was used before, you know, writing 3x is 2x plus x in numerator and denominator to choose your version of cos 2x depending on what else is nearby. And then from there, seeing the algebra through, noticing the common factors, and noticing that that numerator is just equal to negative cos 2x. Okay, so a lot going on here. This is, like I said, tougher than what you would get, you know, on a test, but hey, that's why it's the last question on this assignment sheet. Okay. Any questions on this? All right, so somebody asked for 7 and 9. We can do that. 10, I'm not sure if it was all of them, but you know, let's start with 7 and 9. Unless there's other suggestions, let me know. Okay. So let's take Trig Identities worksheet number 4. Okay, yeah, we'll get to that. So we'll probably do is we'll do 7 and 9, and then we'll go to Trig Identities number 4. And if we have time, we can come back to one of the other ones of 10. Okay, so let's take a look at number 10. So unit 4, assignment number 7. Okay, and again, folks, hopefully we've tried these. Ideally, you know, on a tutorial that's a day or two before the test, we've tried these here. So here this says find the exact value of cosecant of x minus y. Okay, so this is what they're looking for, and they give us a bunch of information. They tell you that x is between 0 and pi over 2. So I'm going to interpret that as x is in quadrant 1. Y is between 0 and pi over 2. So y is also in quadrant 1. And they tell us that secant of x equals 4 over 3. And tan of y is equal to 13 over 5. Now, the idea here is I'm hoping that we recognize this type of question, because we've seen this before where they give us some information about two angles, you know, or sometimes one angle. They don't tell us what the angle is, but they give us the quadrant. They give us one of the trig ratios, and we're able to solve you know, any one of these combinations here. Okay. So first I noticed I don't have a formula for cosecant of x minus y, but of course I have a formula for sine of x minus y. So step number one is turn it into an expression that I can associate an identity to. So this is 1 over sine of the first times cos of the second minus cos of the first times sine of the second. And so essentially I need to find sine of x, cos of x, cosine of y, cos of y, but using this information. So the fact that they're giving me this geometric information tells me that I should be drawing a diagram. So there's my angle x, okay? We shouldn't get thrown off that now we're using x as an angle. It's just a variable. And let's remember what secant is. It's the reciprocal of cosine. So cosine is, you know, the x value over the r value. So that means this is the r value over the x value. So 4 and 3. Okay. And now in order to find sine of x, I'm going to need the opposite side or the y value of this point. And of course, I'm just going to use Pythagoras for that. So this is going to be 16, 4 squared minus 3 squared. And 16 minus 9 is 7. So root 7. So now I can find the missing part. Okay. And I'm going to do something similar for y. Y again is in the first quadrant. And here they're giving me tangent, which is y over x. And so now, if I want to find sine and cosine of y, I'm going to need the hypotenuse or the r value. So this is going to be 5 squared plus 13 squared. So what is this? 169, 79, 89, 194. Okay, this is one of those times where I don't want to take a chance. So here, 5 squared 25 plus 13 squared. There you go, square root of 194. Okay, and now I have enough information to calculate this. So sine of x is root 7 over 4. Okay, again, folks, make sure you're checking all my work here. Cosine of y is 5 over 194, the root 194. And minus cos x is 3 over 4. Makes sense since secant is 4 over 3. And then sine y is 13 over root 194. Okay. So notice here, I just take my time. I just take my time. Okay. But it's very nice because the denominators are the same in the two fractions in the big denominator. So here, what do we have? We have 5 root 7 minus, I guess, 39 over 4 root 194, the common denominator. And now that I have the denominator as a single fraction, I can now take its reciprocal. So that would be equal to 4 root 194 over 5 root 7 minus 39. And that would be a final answer. And I can't say I'm too motivated to rationalize this, but if I did want to rationalize it, who remembers what I'd have to do with the denominator to rationalize that? Take a trip down to back to grade 11. What would I have to multiply the denominator by to rationalize? This is a trick we're going to use in the next course. Anybody?
You'd have to actually, never mind.
So the difference here is you can't just multiply by root 7 to get rid of the root 7 here, because then you're going to get a root 7 there. And the idea, I'm not going to go over it, but just in case you're interested, is you multiply by something that's going to create a difference of squares. So you multiply the denominator by 5 root 7 plus 39. And of course, you have to do the same thing to the numerator. So that when you multiply these two binomials, the middle terms cancel out and you're only left with whole numbers. You're not left with any square roots. But like I said, this is a perfectly acceptable answer for us in this course. Okay, any questions on this here? So really, this is almost identical to something we've seen before. The only difference is it wasn't sine, cosine, or tangent. It was cosecant. So we had to flip that around to get sine of x minus y. But everything else really is exactly the same strategy as we'd seen several times before. All right. Any other questions on this? No? Okay. So let's take a look at 9. Here, unit 4, assignment number 9. And what is that asking? It says an angle X lies in the second quadrant. So even before reading the rest, that kind of tells me a diagram is probably in order. Okay, and tan of X is -4/3. So tan of X is equal to -4/3. And it says determine sine 2x and cos 2x. So sine 2x and cos 2x. Okay. And here, this is actually in some ways looks like it might be an easier question than number 8. Okay. Because I know if I want to calculate sine 2x, I can do that by finding 2 sine x cos x. And then cos 2x, well, I can choose any 3 of the possible versions of that formula, but in the end I'm going to need to find sine and cosine of x. And so here, very similar to what we did before, if tan of x is -4/3, then this is y over x, but I know it's going to be the x value that needs to be negative and the y value that needs to be positive. So this is not going to affect the R value because I'm going to be squaring both of these, but it will affect the signs of the individual trig ratios. So here, I don't really need to calculate this because 9 + 16, 25. So it's the 3, 4, 5 triangle. And now I can go find sine of 2x, which is 2 sine x cos x. Now, by the way, I should know that this answer is going to be positive because it's in the second quadrant, and this answer here better come out to be negative because it's in the second quadrant. So if I don't get that, it means I've made some mistake somewhere. Okay, so here, sine x is going to be 4/5, and then cos x is going to be equal to oh, sorry. Somebody should have stopped me there. We're finding sine of 2x. It's x that's in the second quadrant. 2x is not going to be in the second quadrant. So sorry, this doesn't have to be positive. Sorry about that. Just realized. Now, as I was writing it out, I'm not talking about x, but 2x. Okay, and so here cos of x is -3/5. And so kind of makes sense that if x is in the second quadrant, 2x will be somewhere here. Okay, so here, what do we have? We have 4 times 3 is 12 times 2 is -24/5 times 5, 25. And then cos 2x, well, take your pick. I guess I've already found sine and cos, and since we don't use it very often, why don't I use that version of it just to change it up a bit? So here, what do we have? We have cos x was -3/5, and that's squared. And then sine x was 4/5, and that's squared. So let's see what we have here. We have 9/25 minus 16/25. And so this looks like 9 minus 16, -7/25. Okay. And there you go. So like I said, in some ways, actually a little easier than the previous one. Okay. We didn't have to kind of figure out what quadrant things were in. All right. Any questions on this one here? All right. So the one that was asked for was number 4 on the Trig Identities worksheet. So let's bring that up here. Oh, did I assign that one? Okay, anyways, let's take a look at it. A lot of writing on this one here. So Trig Identities, number 4. Oof. Okay, let's write this out. So cos squared x cos squared y plus sine squared x sine squared y plus sine squared x cos squared y plus sine squared x cos squared y, and then plus sine squared y cos squared x. And we want to show that that's equal to 1. So because there was a lot of stuff here, I'm just going to give a quick look to make sure I wrote it out correctly. If someone else has it in front of them, they can check. That looks good. That looks good. That looks good. And that looks good. Okay. So this looks very messy, but even as I was writing it down, I could sort of see some interesting things here. And I guess we saw this, I think we saw this in an earlier one where, I look at this here, cos squared x, cos squared y, and, I look at this one. This also has a cos squared y. So I can work with these two and factor out the cos squared y's. Or in fact, I've got a second option. I notice when I look at these two, they both have a cos squared x, so that I can factor that out. So these are the things you want to look for. Because one of the things I would prefer not to do is to change any of these into 1 minus sine squareds. And the reason is it's not like, there's only one sine squared and everything else is in terms of cos, or one cos squared and everything else is in terms of sine. Here, they're really all mixed in together. So that's why. So I'll just go with the first one that I found. I look at these two and I see that they have a common factor. Call this 1. And then when I look at the other two, I notice that they also have a common factor of sine squared y. Okay, so that's what I'm going to do in my next step. So here I'm going to start with the left-hand side. Okay, and kind of from number 1, I'm going to look at these two and I'm going to factor out their common factor, which is cos squared y. And what am I left with? I'm left with, on this one, a cos squared x, plus this one here, a sine squared x. And of course, that makes me very happy because I know that that's just equal to 1. Now let me take a look at these two now. And I notice that they have a sine squared y as a common factor. And what's left when I take out a sine squared y? Well, a sine squared x again here, and then plus a cos squared x. And again, that's just equal to 1. So this whole thing, so that's equal to 1, that's equal to 1. So I'm just left with cos squared y, then here plus sine squared y. And again, using my identity, that's just equal to 1. Okay. So again, what you have to keep in mind when you're trying to figure out what to do with an identity is you're not just looking at your identity sheet. You also have to think about what kind of algebra you can do. When we think of algebra, we think of factoring, we think of simplifying, we think reducing, okay? You think of like terms, all these things, a lot of which we've used here today. Okay. So we're just coming up to 5 o'clock. So I think maybe what we'll do is we'll stop it there for now, unless there's an urgent question we want to ask. So I'm just going to stop the sharing, or not the sharing, but the